Hello, everyone, and welcome back to our second session of today, OnlineTestConf Day 2. And let me go ahead and unmute Peter. Peter, can you hear me?
Yes, I can. Can you hear me, Joel?
We can hear you loud and clear.
Great.
Excellent. So you can just start sharing your screen while I briefly introduce you, because I'm sure that you will be able to do it better than I am.
Okay, I think I needed to request remote control first, but
Requested, and I just gave you, so hopefully that will be enough.
Okay, great. So
okay.
I'm going to share the screen.
I'll let you know once we see it. In the meantime, guys, I actually met Peter a couple years ago, I think, in a conference in beautiful Bilbao, Spain. And from the very beginning, I really like his simple and comprehensive approach to testing. And I always like the way that he presents his calls. I remember actually one of the sessions, he got the best session in the conference, and rightly so. And again, I'm very envious of just his way of doing it. And I'm sure that you'll understand what I mean once it's done today. Peter will be talking about cognitive biases, specifically focused on AI systems, but from what I saw, it's something that we can take to other systems as well. So, Peter, I'm not going to stand in your way. Go ahead and take it from here.
Oh, thank you, Joel. You can see my title slide here?
We can see your title slide.
Great.
Clearly
so
enough.
that's a pretty black and white slide, so let's just move on here. A little bit about me, the I Love Me slide. I speak at conferences around the world. I have advanced degrees in mathematics, which is my favorite subject, computer science, and oddly enough, psychology. At this stage in my career, I'm really a technology communicator, but I was formerly also a university professor and technology journalist. I'm a cat owner, you see them there, and also a distance runner, and there's my email address. So what I'm hoping you'll get out of the next 35 or 40 minutes is what kind of systems, how are these systems designed that they produce non-deterministic results based on data, how these results can be biased, and how to recognize and understand bias in machine learning systems. And as Joel says a little bit later, I'm going to expand that and basically say all software systems are biased in some way. We'll talk a little bit more about that later. So what are machine learning and adaptive systems? How can software possibly be biased? How can we tell if they're biased? And really, can we do anything about this? And then I'll summarize and attempt to draw some conclusions. So today, many companies, many enterprises, many government organizations are building a different kind of software. Especially if the system continues to learn in production, it never returns the same result. However, that doesn't make it wrong, oddly enough. So if it returns different results, but it's not necessarily wrong, how do we assess that it is in fact correct? And how do we know if there is in fact a bug in the system? I'm not going to talk a lot about bugs here. What I'm going to talk about is how do we know if it's biased? And what I need to do in doing so is talk about what we traditionally mean by a bug versus what we are referring to when we talk about bias. I have a short definition of a bug here. It's an identifiable and measurable error in the software process or the result. Usually we can, once we identify it, we can fix it with a code change. A bias is a bit more insidious. It is instead a systematic inflection or a slant, let me use the word slant, in decisions that produces results that don't well reflect reality. So it's a trend, it's a slant that produces results that are not the best results. Bias, oddly enough, unlike a bug, bias can't be fixed with a code change. It's a bit more difficult than that. So how does this happen? First of all, our problem domain is usually ambiguous. We're trying to solve a problem, but that problem is not necessarily well defined. And there is no single right answer. There's a range or a set of answers that we can say close enough. Close enough, however, as we'll see, depends on the application, as long as we can quantify that. We don't know quite why the software responds as it does. I was reading about a Google AI recently that has 123 layers of algorithms. Well, how do you trace those code paths, really? How do you go through and say, oh, here's the algorithm that's wrong, especially since those algorithms are adjusting themselves as the software learns, as we train the software. We train the software with data. And what happens is that the software learns from what has occurred in the past, a distinction between what we know has already happened, the input data, and we know what the output is in the past. And so that's how we're training these particular systems. So how can we tell if it's biased? Well, we have to look very carefully at the data that we're using to train it. That's really the key here. We also have to set strict success criteria based on the system requirements. The requirements are key here, and we'll get into that a little bit later. We have to run far more tests than we would in traditional UI or functional testing. We may change the parameters only slightly in a lot of these because we're looking, once again, we're looking for a slant. We're not looking for an obvious bug. And some of those tests will also use radical inputs to say, does the system recognize that the inputs are edge cases or nonsensical or whatever it might be? Then we have to compare those test results to our objectively defined success criteria. So, as I've alluded to, we're training these systems with some data set or data sets. We know what the input data is, and we know what the expected result is based on the past experience, based on our past recording of, based on this, something has happened. What is that something? We know that's something based on our past data. So it's run through algorithms. It's run through layers of algorithms, actually. It may be anywhere between 10 or 12 algorithms and hundreds of different algorithms, depending on how complex the system is. These algorithms adjust themselves as we're training them based on a comparison between what we expect as an answer and what we get as an answer. So we actually run the data through a number of different times. It's in many cases, it's likely hundreds or even thousands of different times as the algorithms continue to adjust themselves. However, what are we actually doing if the data that we're using misrepresents our problem domain? Let's explore that a little bit more closely. I have an example here. It's about Amazon. I read about this one recently. Amazon created an artificial intelligence bot called the web to find job candidates. As we know, Amazon is hiring very fast, hiring probably thousands of people a year. They're not getting enough job candidates. So they built an AI, and they're one of the more advanced companies in artificial intelligence. So they built a bot to crawl the web to find job candidates. Their training data was all resumes submitted to the company for the last 10 years. Once again, that's our historical or that's our past data. However, and it worked for some of the people that they were looking for. However, they discovered that for IT positions, the overwhelming majority of that training data, that past data, were male. So the result is that their AI bot learned that males were superior for IT jobs. And in fact, Amazon had no way, using the data set that they were using, they could not fix that training bias. So, okay, rather than just training with all the resumes submitted, why don't we train with just the people who were hired, right? No, unfortunately, because males were also hired in overwhelming numbers. And Amazon hasn't figured out how to, using what might be considered to be a reasonable set of training data, they haven't found a way to overcome this bias that males are superior for IT positions. So they stopped using this bot altogether until they can figure out a way to, in fact, fix it. So I guess the question here that we have to ask is, does all data, in fact, have some bias or other? You might think there's scientific data out there, there's engineering data that's purely objective, but in fact, depending on which data that we use, we may find that, that the data does have some inherent bias. In fact, in most cases, we'll find that the data has some inherent bias. I'm going to say about 20 years ago, I designed using a neural network, an AI machine learning system. I designed the algorithms for an electronic wind sensor. Now, what happens is that you see the picture there. It has 4 electronic filaments there. And what it does is no moving parts, not an areometer or anything like that, just no moving parts. It determines wind speed and wind direction based on the cooling of these filaments, based on how fast the wind is blowing and in what direction it's blowing. So I designed a fairly simple, well, it wasn't simple at the time, but it was today it would be considered a simple 3-layer neural network. And then I used known data to train it. We actually put this wind sensor through and the filaments through a wind tunnel. So we knew what the wind speed and direction was, and we could record the cooling in degrees of all 4 of those filaments. And that gave us a result, a known result of wind speed and direction. So I used that data to train this neural network. That's pretty objective, isn't it? Can this, in fact, possibly be biased? Well, yes, it can. In fact, what we did was we created the training data so that it was recorded in the wind tunnel with a single temperature, a constant sunlight and constant humidity condition. And once this got out into the field, we realized that the real world isn't like that. The real world has different sunlight conditions. The real world has different humidity conditions. And turns out that affected the results. Okay, so it's a bias, but it doesn't hurt anybody, right? So maybe I could have gotten more exact if we had recorded the wind tunnel data under different temperature, sunlight, and humidity conditions. It doesn't hurt anyone, or does it? Does anybody remember, now I'm dating myself a bit here, but in 1986, the Space Shuttle Challenger blew up upon liftoff. And the problem was that the temperature caused a different type of characteristic in a rubber O-ring that was used as a part of the construction of the fuel tanks of this. And as a result, the O-ring did not behave as expected, and it caused an explosion. Something as simple as that. So where do biases come from then? Where can we find sources of bias? Data selection is probably the most common source of bias, in that we choose our training data that represents only one segment of the domain. We limit the data to certain times of the day or seasons of the year or whatever it might be. Or we may select data that overrepresents one population. And that was kind of Amazon's problem there. Their training data overrepresented the male IT applicant. Or it's possible that the problem domain has changed since our past data has taken place. Maybe we have more female graduates in IT now than over the last 10 years. I don't know if that's the case, but maybe the problem domain has changed in some way so that our data no longer reflects the problem domain that we're testing. So a second source of bias is what I'll call latent bias, in that ideas, concepts become correlated when they really shouldn't be correlated. What we fail to realize, and unfortunately, in many of these machine learning systems, what we're really looking at is correlating that input data to our output result. But that doesn't mean causation. And the cartoon here is really good at illustrating that. It says in the first one, two males saying, one of them's writing mathematic equations on the board. Wow, you suck at math. And then the second one, it's a male and a female, and she's writing equations on the board. And he, I'll say, overgeneralizes, saying, wow, girls suck at math. And what we could be doing is promoting stereotypes. That was another one of Amazon's problems here, in that their training data promoted a particular type of stereotype. The third is interaction bias. And this occurs when a human being is interacting, usually verbally, or it could be typing in, or something like that. But we focus on words that are being applied using slang or unusual words to describe a situation. That's bad, man. What does that mean? What the heck does that mean? That could mean that something is really not nice, or something is incorrect, or something like that. Or it could mean, boy, admiration, because that's a really elegant algorithm. This is the story of Microsoft Tay, and I'm going to ask, and I don't expect an answer from you folks, but how many of you have heard of Microsoft Tay? This was about a couple of years ago. Microsoft released a Twitter bot that was supposed to learn from interactions on Twitter. And what happened was the people caught on very quickly that Tay would learn to respond based on what they sent to Tay, based on what they tweeted to Tay. Say that one 3 times real fast. And as a result, within a day, Tay became racist, sexist, obscene, whatever it might be, and Microsoft had to withdraw it from Twitter. And the story of Tay is that it wasn't bad, it was just trained that way by the Twitter community. So why does bias matter? Why do we care about finding bias? Well, first of all, we could get wrong answers that are not are just not the right answers at all. And so, for example, you could go and apply for, I'll say, flood insurance or something like that. And your insurance company comes back and says that you denied flood insurance. And you ask, quite reasonably, why? And they can't say other than, our algorithms rejected you. Well, that's not a very satisfactory answer. Bias also matters because we could have some subtle discrimination here. Could be legal discrimination, could be illegal discrimination, but it's so subtle that nobody can identify it and nobody knows it. Or we're not getting it right often enough. We're just, sometimes we're just missing because of our slant. How are these types of intelligent systems being used? Well, they're being used in transportation and self-driving cars, such as the Google autonomous vehicle here. In e-commerce recommendation engines, in finance, high-speed trading, stock trading systems, things like that. HR. This was a scary one for me because I was reading fairly recently that more and more companies are using commercial AI systems to not just screen resumes, but also actually have phone calls, screening phone calls with candidates. And some of these actually advertise that you can actually use their commercial software to not just pick out resumes and screen the people on the phone, but actually go through the entire hiring process without actually talking to a single human being, and actually hire somebody based on the recommendation of the AI. Medicine, this has the potential to be even scarier. Medical diagnostic systems, for example, where if they are used to diagnose and treat, errors or biases here can actually can be life-threatening. And here I'm now going to leave just for a moment, say it's not just AI that has bias. All software has biases because software is written by people. Software developers make hundreds of decisions on design, variable use, memory allocated, things like that, every single day as they're writing software. They make decisions on how to design that software and how to implement it. And people are biased, so at least some of those decisions are going to be biased as well. Can we find it and correct it? And in fact, do we have to? So there's an interesting question that we'll get into a little bit later. I like this one. So a London doctor can't get into a fitness center locker room. They use smart cards to identify the person and to allow access into various facilities in their gym. While acknowledging that, yeah, this is a problem, the fitness center couldn't understand why it was happening and couldn't fix it. But finally, after, I'll say, a number of months where she could not use her smart card, it turns out that the software development team could identify the problem. What they did was, as you register for this, for a membership in this fitness center, one of the first things you are asked to choose is your salutation. Mr., Ms., Mrs., Doctor. And it turned out they had hard-coded doctor to be synonymous with male. At the time, it was just meant as a convenient shortcut. But clearly, that was a bias. The software development team associated doctor with male. So believe it or not, she could get into the men's locker room, but I don't think she ever tried. Now about that data. We're making heavy use of data. We're counting on data to tell us to get accurate, to be accurate in our AI and machine learning systems. In some cases, scientific measurements are accurate, but we could be using actually the wrong measures. Or in my case with the wind sensor, it wasn't fully representing our problem domain. It did not behave as expected in the wild. But a lot of data that we're using in developing AI systems today is also subjective. We train face recognition with photos of one race overrepresenting another. We train with our own values of beauty. What is beautiful? This is beautiful. The old website, Hot or Not, we could use data like that, but that's biased. Another example is recommendation engines. Other people bought this. You may also be interested in something else. They're useful in that I'm sure Amazon makes over $1 billion additionally a year by recommending other products. But they can be very wrong sometimes. And they're wrong in that the algorithms think that we want to see what they show us. So I'm a distance runner, as I mentioned at the beginning here. I use, for my running, I use a brand called Brooks running shoes, and they have a particular model called Ghost. So about a year or so ago, I ordered some Brooks Ghost running shoes on Amazon. And I got you may also be interested in Ghost costumes, Ghost hunting equipment. The recommendation engine that Amazon had at that time did not take the context into account. They did not realize that when I talked about Ghost as a running shoe brand name, that I was actually talking about athletic gear. Instead, they thought I was talking about literally ghosts. So the problem starts back in requirements. So what does it mean to be correct? how is this really going to work in production? We need to be very, very specific in looking at our requirements. How do I test for bias? I can look at outputs for given inputs and set accuracy parameters. The outputs, I can say, looking at a normal curve, maybe 95 out of 100 answers have to be within a certain range. Don't even look at the outputs at all, and instead look at traditional functional or non-functional types of results. Because if we haven't defined the requirements well enough, we can't test for accuracy. Or maybe we just throw up our hands and go home. We can't easily define bias, let alone test for it. I think we can test for it, but it's going to be very difficult. So how do we do that? First of all, we need to set objective, very objective. I will accept this answer plus or minus. I will accept 95 out of 100 results within a specific range. That's going to be very dependent on the problem domain. 95 out of 100 may work for an e-commerce engine, recommendation engine, but it won't work for an autonomous vehicle, a self-driving car. We need to test not with the same data we used for training, but we need a new data set. And one of the things, once again, 20 years ago that I used with the electronic wind sensor was I actually divided my data set in half. And that half the data I used to train the data, and the other half I used to test the resulting system. Don't count on all your results being accurate. You also need to understand how the network, how the AI system is architected as a part of the testing process. And you can't communicate, yes, this test passed or this test failed, or many tests passed, a few have failed. Instead, we've got to communicate our results to the stakeholders in the level of confidence that we have in the results. So how do we gear up the test? We need to think different. First of all, and this is vitally important, we need to understand what our users expect. What would a user do with this application? What decisions an AI user would make with this particular application? You need to know how your training data and your testing data, how it was collected, under what circumstances it was collected, under what environmental conditions it was collected. You need to write many tests to look for trends, and specifically you need to write tests to exploit edge cases. You need to look at, for example, if you're testing, something like Amazon Alexa, you need to come up with interactions that represent things different than what people may commonly ask Alexa. So what's a bug? It's a mismatch between inputs and outputs, but in many AI systems, it's supposed to be that way. Not every recommendation will be a good one. Not every answer will be a correct one, but that doesn't mean it's a bug. So we need to be very specific as we're looking at requirements and we're looking at our test results. We need to be very specific about how many correct and versus how many incorrect answers we'll accept. We found a bug. It could be unrelated to the neural network. If the neural network is involved, once again, we need to be able to quantify this. And for testers looking at AI systems or looking for bias in general, even with non-AI systems, you need to be very quantitative about how you define this. You're going to be using basic college-level statistics to say 95% of the time, or 2 standard deviations, or 3 standard deviations, or whatever it might be, within a particular range. You need to understand your basic statistics and apply them in defining your requirements and analyzing the test results. If in fact you do have a problem, it could require, once again, it's not a code change, it's am I using the wrong, have we used the wrong data set to change it, to develop this. And if you have, it may result in going back and finding a better data set and training the application all over again. Bias and truth and AI, oh my. All of our decisions are, in fact, everybody's decisions are biased in some way. I'm biased, you're biased, he, she, or it is biased. So in our AI systems, and looking at this from a broader context, from our AI systems, do we want the best decisions? Do we want the best answers? Or do we want the answers that a typical human would make? Because human decisions do come with human biases. Can we get those biases out of our software? Will we get better results if they do? In fact, even with bias, computer decisions may be better, and I'll go back to the whole medical diagnosis thing. If it's a consistent bias, rather than how the doctor or how the diagnostician may feel that day, if it's consistent on a day-to-day basis, the AI system, even if it's biased, may be better than the human expert decision. So, do we want to, all that being said, do we want the system to give us the best answers or to replicate how we would decide, even if there is bias in it? We may, as I said in the last slide, we may accept bias if it's consistent rather than seemingly spurious. This is a question with no easy answer in practice. So any team, any organization developing an AI system has to answer these larger questions before they even embark upon down that road. And for example, in many cases, computers and human experts perform differently. I'm going to date myself again. I was 13 years old in 1971, sitting in Forbes Field in Pittsburgh in the United States, where in the bottom of the ninth inning, ball player Roberto Clemente stepped up to the plate and hit a home run that won the game for the Pittsburgh Pirates. Now, Roberto Clemente was not a power hitter. He was a very good hitter for average, but he was not somebody who could be called upon to hit a home run. He recognized the importance of the event, his at-bat, to the Pittsburgh Pirates, and they did win the World Series that year. He recognized the importance of him winning the game right then and there. And he delivered in the clutch, as we say. He delivered a win for the Pittsburgh Pirates that day. Humans can recognize the importance of some events, and sometimes they can rise to the occasion. Machines, on the other hand, treat all events as equal. We have no we can teach a machine to recognize that some events are more important than others, but we can't then substitute a better algorithm so that they'll perform better. If there is a better algorithm, the AI system should be using that algorithm at all times. Machines cannot deliver in the clutch. They cannot rise to an important occasion. This is less a bias than an inherent weakness in machine systems. And this is one of the reasons why there will be not so much machines making decisions, but a partnership between AI systems and human users. We don't fully understand our complex software systems, including AI systems. And disasters can happen because software behaves in unexpected ways. The airliner crash in Lion Air in Indonesia of a month or so ago is one very good example of that. Human oversight may prevent those disasters or may prevent day-to-day wrong decisions. The problem is that sometimes machines respond too quickly, and in some cases, there's not enough time to apply that human oversight. But I am a very strong believer in the human in the loop. So you may, after all of this, you may have some objections here. You may say, for example, I'll never encounter this type of application. I'll never encounter an application that's biased. I work on internal accounting systems or internal SharePoint applications or something like that. You might be surprised. Your CEO may read an article in an airline magazine about AI and come back and says, we're going to start using AI. Right now, just over the last 2 years, AI has surprisingly moved into the mainstream. So I'm going to say, if you have not seen an AI system in your organization yet, you will within the next couple of years. You may say, I'll just do what I've always done. No, you won't. You need to think very differently in testing AI systems and in looking specifically for that bias. Maybe you'll say, my goals will be defined by others. I'm just the instrument who executes what others tell me to do. In the case of AI systems, they may be counting on you to do the best you can. You may, in fact, be the one. So, code is not intelligence. We are not yet building intelligence from code. Even though we call them intelligence systems, machine learning systems, and things like that, they're still software applications. We are not making them intelligent. And you really can't make intelligence, at least at the current state of technology, from code. Algorithms are thoughtless. They can never look at what should be done versus what the algorithms tell them to do. Specifically, learning systems are what we program and what we train. They're no more or no less than that. They don't acquire a life of their own. They're not, in any sense, more nor less than the data that we put into them. There's no easy answer to any of this, but you need to be cognizant of the fact that you're gonna, if you haven't already, you're going to be testing intelligence or machine learning systems at some point in time. I'm going to guess in the next 2 or 3 years, but certainly within the scope of your career. Also, if we choose the data will likely be biased in some way. So you have to look very, very carefully at how the data set that you choose fits into your problem domain. Does it adequately cover your problem domain? Does it overrepresent one part of the domain over another? And things like that. So in wrapping this up, I'm going to take a line from Indiana Jones and the Last Crusade here, where the Templar Knight says to Indiana Jones, you must choose, but choose wisely. I've got some references here, and since the presentation will be available for you to view online, and if you want, contact me and I'll send you the slides. There's nothing copyrighted about them or anything like that. But some things you might want to read about bias in AI and machine learning systems. So that's all I have to say right now. Here's my contact information, and here's where I tweet at. So, Joe, I'm going to turn it back to you at this point.
Thank you very much, Peter. I really, as usual, I really like your sessions. Wait, let me capture so that people don't see a blank screen for a second. Wait, now I don't see my Zoom, obviously. And now I see my Zoom. Just one sec. Peter, I had a question that actually popped to mind. And, you know, there's this big battle, hey, is testing dead? Is automation gonna eat us alive? Stuff like that. And all of a sudden, you talk about biases. And you talk about, hey, we actually need to put a lot of thought in our data and the learning mechanisms that we're putting and testing that and adding statistical analysis, either stronger or weaker than that. But is this actually that place that explains why there are still going to be things that we will not be able to automate? Or do you start seeing places where you can use some sort of scripting coding or automation that will help us to test even AI systems that might be biased in a sense, meaning to detect that bias using all sorts of systems like those?
That's a very good question, Joel. And I actually had somebody suggest to me who was looking at this presentation. I had somebody suggest to me, we're going to need AI systems to test AI systems.
And you know, I was talking about that with someone here in the company, and I said, well, but then you need to develop basically two competing algorithms to do basically the same.
Mm-hmm.
Because you cannot test the same algorithm with the same algorithm, because then the bias would actually reflect itself. But so other than that solution, is there anything else that we can do?
So I think that, like I said, so I think that AI and machine learning applications are actually creating the ability, creating if I could say it, a brave new world for testers. I think it's starting the golden age of the domain specialist tester. 20 or so years ago, we had a lot of testers coming in from, I'll say, the business units who were experts in their particular line of business, who got involved and interested in technology and moved into testing as a result of that, but weren't trained as testers or anything like that. I think today what we're really seeing is we need that person back again. We need vitally somebody who understands the problem domain and the end user.
Okay. There's a question here by one of the presenters yesterday, by Louis Gibbs. Do you think that there is a risk of bias in testing AI as well as in training the
AI? Yes. Well, like I said a few minutes ago, Joel, all software is biased. We may not recognize it, but all software is biased in some way. Developers, development teams are making literally hundreds of decisions on what variable to use, how to structure a particular routine, and things like that. And their decisions are based upon their experience and what they feel is best, but objectively, it may not always be the best. In fact, usually it may not be the best, but it's what they know. It's what they were trained in, perhaps, and once again, bias in developer training, perhaps. So, bias is everywhere. We're not going to completely eradicate people from bias. We're not going to completely eradicate software from bias. Our best bet is to recognize it and try to get our software to be, especially our AI and machine learning systems, try to use data that best reflects our problem domain.
Sounds great. So, Peter, the only thing left at this point is to echo the comments on the Slack channel saying that it was a great presentation, and I also learned quite a lot from it. So I want to thank you for that. And again, just thanks for being here and for sharing your thoughts.